Hello and welcome. This webinar is called A Better Way to Use MATLAB for Test Data Analysis. As Amanda said, my name is Joe Spadola. I am an applications engineer for HBM nCode. And today we're going to be talking about how we can leverage the powerful numerical computing capabilities of MATLAB to create a robust and easy to use and maintain process for analyzing measured test data within the nCode GlyphWorks software environment. So this is our agenda for the next 20 or 30 minutes or so that we have together. I will start by giving a brief background on MATLAB, which I will assume most of this audience is very familiar with. I will then introduce you to a piece of software called GlyphWorks, which is developed by the company that I work for called nCode. And I will assume that this audience has a very limited, if any, familiarity with nCode or GlyphWorks. Then I will introduce you to a function inside the GlyphWorks software called the GlyphWorks scripting glyph, which is what allows us to bring MATLAB functionality into GlyphWorks. And I will finish off by giving two live demonstrations, one showing an extensive built-in digital signal processing power of GlyphWorks, and the other showing a MATLAB script actually executing inside the GlyphWorks environment. Okay, so let's talk for a second about MATLAB. As I said earlier, I assume that most of you will already know this, but I will summarize anyway. MATLAB is a high-level numerical computing environment developed by a company located just outside Boston called MathWorks. MATLAB is designed for, among other purposes, algorithm development, matrix math and manipulations, data analysis, and data visualization. You run MATLAB by executing command line codes, either one at a time in the environment or by packing these functions or codes together into a written script, which is more commonly referred to as an M file, and running that M file against some data. The results of that analysis are then saved to file, printed to screen, displayed as plots, etc. So I don't think that should be too surprising to anyone at this point. Okay, so now I'm going to shift gears a little bit and step away from MATLAB for a second and spend a few minutes introducing you to some software that you may have never heard of before called GlyphWorks. GlyphWorks is one of three software products developed by a company called nCode, and it serves as a data processing system designed for analyzing measured test data. nCode as a company has two other software products, one called DesignLife, which serves as a fatigue analysis tool in the virtual CAE domain. And what it effectively does is, with a few user inputs, it turns an entire model's stress plot into a life plot. Okay, so a very powerful tool in the virtual domain. Our third product is called Automation, and it serves as a database for managing and storing large amounts of test data. The unique feature about Automation, however, is that this software I'm talking about called GlyphWorks lives underneath it and can automatically process data as it's uploaded to the Automation server. Since our focus today will be GlyphWorks, I'm going to dive a little bit deeper into its capabilities. As I've said already, GlyphWorks is a data processing system designed to analyze measured test data. It has a very powerful and easy-to-use graphical interface with drag-and-drop capabilities. We can deal with data in both the time and frequency domain. The processes we build are easily scalable and can handle, without problem, large channel counts. We're talking hundreds to thousands of channels and huge numbers of tests at the same time as well. It has something called one-click reporting capabilities, which I will demonstrate later, that allows the user to very efficiently and quickly generate a report of customizable results. GlyphWorks has a wide range of built-in digital signal processing tools such as filtering, mathematics, statistics, signal editing, anomaly detection, Right? The only thing that's consistent about measured test data is that it's never perfect. So GlyphWorks can automatically help look for problems like spikes, flat lines, drifts, all sorts of problems you might run into when measuring actual data. GlyphWorks can automatically plot on a map GPS traces to help users in the ground vehicle industry correlate events of interest in space and time. GlyphWorks has a vast array of built-in fatigue analysis capabilities as well, such as stress life, strain life, and crack growth analysis. We can perform fatigue-sensitive time series editing to help accelerate lab or rig tests. We can perform fatigue analysis for entire proving ground schedules or complete flight spectra for the aerospace industry. We can also look at fatigue in the frequency domain and create accelerated vibration shaker profiles. Okay, we also have a variety of tools for noise and vibe analysis. So what I've just described is a relatively small subset of all of GlyphWorks capabilities. We actually have over 100 built-in, highly configurable engineering functions ready for use inside GlyphWorks. Okay, so now that we know we have methods and processing capabilities to process data, what kind of data are we talking about, and where does this data come from? Well, today, data comes from all over the engineering world. The most typical and probably most common source of data is measured test data in the form of strain gauge histories, accelerations, displacements, forces, GPS, CAN bus data, etc. That's been measured in the lab or field. It comes off a data acquisition box as a file, and depending on what type of data acquisition system you have, it could be in any number of different formats. More frequently, and with the advent of higher desktop computing power, we are seeing more and more data come from the virtual world. That is in the form of finite element analysis, such as solved structural FEA models, harmonic analyses, etc. These come from FEA packages such as ANSYS, Nastran, Abacus, etc. We're also seeing data come from multi-body dynamics simulation tools such as MotionView or Atoms. And all of these different sources of data mean that we have all sorts of different formats of data. And that, in and of itself, can actually pose a significant challenge. How do we effectively retrieve the data we're interested in from all of these different types of files and engineering domains? GlyphWorks natively supports and reads 38 different industry file formats, and we have the ability to write over 15 formats as well. So what does that mean for a MATLAB user? Well, it means that you no longer have to code your own file readers just to analyze data. Okay, GlyphWorks automatically supports these industry standard formats from all of these data sources, and the easy-to-use drag-and-drop GlyphWorks interface allows you to literally just drag and drop your data into a workspace and start the real engineering work immediately. And we'll see just what I mean by that in a few minutes. Okay, so now we know that we don't have to spend engineering resources coding file readers. We can instead spend our engineering resources doing actual data analysis. I've explained already that GlyphWorks has a vast amount of built-in engineering functions, but for now I'm going to focus on how we can specifically build MATLAB functionality into our GlyphWorks process. We accomplish this with a tool called the GlyphWorks scripting glyph. As you can see in the red highlighted box, the GlyphWorks scripting glyph exists as a function in what we call the glyph palette. And we will find, if we look in there a little more closely, we'll find a glyph simply called MATLAB. To enable the MATLAB scripting functionality in our process, simply drag and drop the glyph onto the workspace. In the process shown on the screen, this has already been done. Once we have the MATLAB scripting glyph on the workspace, you can either write from scratch or copy and paste your existing MATLAB code right into the glyph as shown. You interact with upstream data and send your results to downstream glyphs or other engineering functions by the GlyphWorks API. And we'll see that in a minute. Okay, so how does this all come together? I'm going to now jump into the software for a minute and show you two live demos. Now, the first one does not actually make use of the MATLAB scripting glyph, but instead I wanted to serve as a demonstration of how simple it is to create from scratch a fairly complex engineering analysis. So in this specific example, I'm going to shorten a time domain rig test by removing non-damaging content from measured strain gauge channels. Okay, and what I kind of want you to keep in mind while I'm building this process is one, how easy it is to do in GlyphWorks, and two, how much time it might actually take to code something like this from scratch solely in MATLAB. So I'm going to jump over into the nCode software real quick, and I am using a software from nCode called GlyphWorks, and this is what the GlyphWorks environment looks like. On the left here, we can see the what is called the available data window, and in it we can see a couple of data files. Okay, any file that GlyphWorks recognizes, and I talked earlier, there's 38 different formats that we recognize. Anything it finds in the folder that I've pointed to will automatically load into this available data window here. And GlyphWorks is smart enough to organize it by the file type. So here you can see I have two types of time series data. Data that has been measured on some sort of data acquisition device, and it has a constant sample rate. For this particular example, I'm going to be looking at data that is in the form of, it's a stiff format, and it's some measured strain gauge data. So to get this onto the workspace, like I said earlier, literally just drag it from the available data and drop it onto the workspace. Now I have that data available for me to use and work with. To view the data, I can just click on this display button here, and it will populate the display as shown. There are a number of different ways to view this data once you're actually looking at it, or to manipulate it rather, once you're looking at it. For the meantime, I will just maximize it to show you kind of a close-up view of what we're actually looking at. So here we have over 580 seconds of measured strain gauge data. Okay, and like I said, what we're going to try to do is remove the non-damaging content from these channels. Okay, so to do so, I am going to go over into my glyph palette on the right side of the screen here. This is where all of the standard GlyphWorks engineering functions live. And I'm going to go to the fatigue palette right here and pull out a strain life fatigue analysis glyph. Just like we got the data onto the workspace, I literally click and drag and drop my strain life glyph onto the workspace. And to pass data between glyphs, you simply click on these output pads and pipe the data into the glyph that you want it to go into. So here I'm sending my data that I've taken from the available data, and I'm passing it into this strain life glyph that I just pulled out into the workspace. From here, I am going to also grab what is called a damage editing glyph and drag and drop it onto the workspace as well. The strain life glyph here is actually doing a strain life analysis on this measured strain gauge data. One of the outputs from that analysis is called a damage time series. It's showing me where in this original input file damage is occurring, and I'm using this damage editing glyph here. Once I send that information to this glyph here, I'm using this damage editing glyph to highlight for me in another tool we have called the graphical editor, where those damaging cycles occur. So I'm going to pass to the graphical editor the original time series data that we have. I'm using the strain life glyph to calculate where damage is occurring in the original file. And then I am sending that information to a damage editing glyph, which will highlight for me the areas of interest. Okay? The output of this will be a shortened time series of the strain gauge with only the damaging parts of the original file. Okay, so one thing that I need to do, I need to go into these glyphs here and change a couple of settings. First thing I need to do, anyone who's done a fatigue analysis knows that one of the required inputs is material properties. So I'm going to go into the strain life properties glyph here. I'm going to go to the materials tab, and doing so exposes all of the strain life material properties that we have available for us in that come standard in GlyphWorks. For this analysis, I'm going to choose this carbon steel right here. So I simply click on that, click OK. I'm going to change one more setting in my graphical editor. And now the process is ready to run. To execute the process, I simply push this play button up at the top, and the flow runs as such. Okay, so I have input data on the left. I've done a strain life fatigue analysis, used an output from that glyph to highlight for me in this graphical editor where non-damaging content exists. I'm using this graphical editor to delete that data, and the output is then simply, if I expand this a little bit, a shortened time series of nothing but the damaging content of the original channel. So you can see we are now looking at only about 58 seconds worth of data as opposed to the original 580. Okay, so we're cutting a test down from about 10 minutes of original data into less than 1 minute. So we're cutting it down to about 10% of the original length of data. Okay, I'm going to minimize this glyph again. And real quickly, I talked about the one-click reporting capabilities of GlyphWorks. So what I'm going to do real quickly is drag out what we call a studio report, which is a pre-configured display of various results from my analysis here. Okay, I'm going to send in the original time series data. I'm going to send in the modified time series data, which comes from this glyph here. I'm going to send in the some information from the test. I'm going to send in the original time series data. I'm going to extract some information about the shortened time series data, and I'm also going to look at how much damage from the fatigue glyph has actually been retained in this analysis. Now, when I run this file again, you can actually see this report that I've created actually steps through every single channel I have and prints out a nice report for me. There are many different options in report export types. For this particular one, I've decided to export each channel on a new page in a PDF form. So if I go to the original file, or the original folder that I'm working in, I can see there's now something called report-export.pdf. If I open that up, I can see each page contains that information from different channels. Okay, and it shows me how much data has been cut out. So it shows you the original length of the time series file as well as some other information. Okay. So what we've seen is a very quick demonstration about some of the advanced time series editing capabilities within GlyphWorks. Here we've incorporated a fatigue analysis. We've incorporated intelligent fatigue-sensitive time series editing. and we've generated a report very simply. Okay, so I'm going to jump back to the presentation for a second. And now I'm going to go into the second demonstration. And in this one, I'm going to actually show how MATLAB and GlyphWorks interact together. Okay, so I've been talking about how we can do that, so now I'm going to actually do that. The situation I'm proposing or setting up is as follows. Let's say I need to know for some calculation the acceleration history at the center of gravity of my engine. Let's pretend this is an engine that I'm analyzing. Unfortunately, it's impossible to put an accelerometer at the center of gravity of my engine. So what can I do? Well, I know that I can place accelerometers at various locations around my engine that are not located at the center of gravity. And doing so, I will be able to build what I'll call a translation matrix that allows me to relate these, quote, remote accelerations to the actual accelerations at the area of interest, in this case, the center of gravity. So you can see in this picture, I'm showing these triaxial accelerometers in different locations throughout the engine. And what I do then is build that translation matrix. So doing so looks a little something like the following, where these values A0, B0, and C0 are the distances from the corresponding accelerometers to the engine center of gravity. The remote accelerations on the right are the accelerations that I can actually measure. So this is going to be the measured time history from those accelerometers I showed on the actual engine. And the engine CG values, that green matrix there in the middle, are the values that I'm looking for. Okay, so following the basic rules of matrix math, I know that I can solve this linear system of equations for that engine CG accelerometer matrix, which are my values of interest, by inverting this translation matrix and multiplying by the remote accels. Okay, so if you remember from your college days, invert and multiply is how you solve for this engine CG accel matrix. So doing so leaves me with the following. Now, if there's one thing I know about MATLAB, it's that it's fantastic at performing quick matrix manipulations, which it turns out that is something that GlyphWorks is actually unable to do with a standard function. So this is a perfect application for incorporating MATLAB scripting into a GlyphWorks process. So let's see that in action. I'm going to jump back into the software now. And I'm going to create a new process, or I'm going to clear that process away. And I'm actually going to open up one that I've already created. Okay. The input to this analysis will be the measured accelerometer data that I showed from the engines. And you can see I have already have that data loaded in my available data window. Here it's called SWXL 3 triaxial data. So I'm just going to bring that into the workspace by dragging and dropping it into this measured remote acceleration glyph. And I can display that data by looking at it here. And if we take a second to expand it, we can see I have these 3 channels contain my X, Y, and Z acceleration. If I look over and pan through some of these other channels, I can see here's my accelerometer B, X, Y, Z acceleration, and my accelerometer C, X, Y, Z accelerations. So here I have about 30 seconds worth of measured acceleration data. I have shown the equation required to solve this equation, this linear system of equations, and I do that with MATLAB. So I have this MATLAB glyph out on the workspace, and I said earlier that I can access the the code in there by going and exposing its properties. So let's do that right now. So here you can see all of the actual MATLAB code exposed in this glyph. Okay. Now, when I run this process, this code is executed at runtime. Okay. Now, you can actually see in here some of the actual matrix math going on. If I scroll down just a little bit, we can see a pseudo-inverse being calculated here on line 36. If I annotate that, so we've got a pseudo-inverse calculation going on right here. And if I scroll down a little bit farther, we will find some more matrix math. But for the time being, I will just leave it at that. So our MATLAB code in here exists. We have our input data, and our output data, as I said, are going to be our engine CG accelerations. So just like the last process, all I do is click Run, and in a quick second, you can see MATLAB actually being invoked on my taskbar, and the calculation completes. So now I have a series of engine accelerations, or measured accelerations, or calculated accelerations at the engine center of gravity. Now, to just quickly show how easy it is to incorporate some other standard glyphs into this process, let's say I've done this calculation, but I realize that there's some high-frequency content in the measured accelerations that I want to filter out of this analysis. Okay. One way you could do it is go in and build a filter into the MATLAB glyph and edit the original code and try running it and hope that it works. Additionally, you can, or I should say, in contrast, you could use the GlyphWorks built-in functionality to do that for you. So I'm going to go over to my basic DSP glyph palette over here and look for something called the Butterworth filter. To use this filter, I do nothing more than drag and drop it onto the workspace, and I'm actually going to insert it in between the measured accelerations and the MATLAB scripting glyph. So I simply right-click and disconnect that data connection, and then just plug this in between. Okay, now if I run the process again, there's my filter, the analysis is complete, and now I have filtered data actually being run inside the MATLAB glyph instead of the data that contains all of that content that I wasn't necessarily interested in. Okay, so I'm going to jump back to the presentation now and finish up here. So what does this mean to you? Well, you've been introduced to a very powerful data processing tool called GlyphWorks that contains over 100 pre-built, highly configurable engineering functions that don't require programming knowledge to use them. You saw how easily I just incorporated that the filtering into that analysis in literally a matter of 5 seconds. Okay. These glyphs or engineering functions are incorporated into a very intuitive graphical drag and drop user interface that's easy to edit and maintain and can easily handle large amounts of data. We've also seen how the standard GlyphWorks functionality can be extended to include the complex numerical capabilities of MATLAB. I showed an example of matrix inversions, but we can also use it to easily embed proprietary in-house codes into a GlyphWorks process to streamline and standardize your data analysis. So the idea is to use GlyphWorks for what it's good at, which is data handling, basic DSP, using all of the pre-configured engineering functions and algorithms, and then using MATLAB for what it's good at, which is what I term here heavy lifting, or in other words, the complex numerical analysis. So the idea is to use the two together in your engineering process.